When you first encounter Linux as a beginner, it is tempting to think of it as a collection of programs you run, and the operating system simply keeps them going. Then you notice that many programs start automatically. Some start only when needed, some restart when they fail, and some are tied to the boot process in ways that feel almost like choreography. The tool that coordinates most of that modern choreography on many Linux distributions is systemd, and the most useful way to learn it at exam level is to focus on its unit model rather than specific commands. A unit is a definition of something the system can manage, like a service to run, a timer that triggers work, a mount that attaches storage, or a target that represents a desired system state. The reason this matters is that systemd is designed to express relationships, so you can describe what should be running, in what order, and under what conditions, instead of relying on scattered scripts. In this episode, we build a beginner mental model for unit types, targets, and dependencies, and we connect that model to the kinds of reasoning Linux Plus questions often demand. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A unit is best understood as a structured description of an object that systemd can start, stop, monitor, or otherwise coordinate. The most famous unit type is the service unit, because services are long-running processes like web servers, time synchronization clients, or background daemons that provide functionality continuously. But systemd manages more than services, and that broader scope is what makes it so central to modern Linux. Timers are units that trigger actions on schedules. Mounts are units that describe how file systems should be attached, and targets are units that group other units into a meaningful state like multi-user operation or a graphical environment. Each unit type exists because system behavior is not only about running programs, it is also about timing, dependencies, and readiness. For a beginner, the important shift is to see system startup as a dependency graph rather than a simple linear list. Once you see the graph, concepts like targets and dependencies start to feel natural instead of mysterious. Service units are the units most people mean when they say systemd service, and they represent something that should be running and supervised. A service unit can describe how to start the program, how to stop it, and what counts as success or failure. Systemd can also take actions when a service fails, such as trying again, which is part of what makes it feel resilient. At exam level, you should understand that services are defined so the system can manage them consistently, and that management includes startup order, restart policy, and whether the service should come up automatically at boot. Another key idea is that not every service is meant to run all the time. Some services are designed to start on demand, triggered by other system activity, which reduces resource use and can reduce attack surface. Even without going into implementation details, you should connect service units to the idea of controlled, policy-driven background behavior. Timer units are systemd's way of expressing scheduled actions using the same unit framework, and they connect directly to scheduling concepts you may have learned earlier. A timer unit defines when something should happen, and what it triggers is often another unit, frequently a service unit that performs the actual work and then exits. This separation is important because it makes the schedule and the work distinct objects with clear roles. At exam level, you do not need to memorize timer syntax, but you do need to understand why timers exist. They integrate scheduling into systemd's dependency and logging model, which can make scheduled work more consistent and easier to track than ad hoc scheduling approaches. Another concept to keep in mind is that some timer designs can handle catch-up behavior, depending on the intended semantics, which is why systemd timers are often discussed alongside other scheduling tools. The key is to understand that a timer is not the work, it is the trigger, and systemd treats both as units so they can be managed together. Mount units describe how file systems and storage should be attached into the directory tree. And this is a big deal because many services assume storage is available before they start. If a service expects a configuration file or data directory on a particular file system, but that file system is not mounted yet, the service can fail in ways that look like missing files or permissions problems. Systemd mount units exist so mounting can be expressed as part of the same dependency graph as services. This means you can represent the relationship. This service requires this mount, in a way the system can enforce at boot. For a beginner, it is helpful to remember that Linux treats storage as directories, and mounting is what connects a physical or logical storage device into that directory structure. If the mount is missing, the directory might still exist, but it might point to the wrong place, like an empty directory on the root file system instead of the intended storage. That subtle difference can create confusing symptoms, which is why mount readiness is a meaningful dependency. Targets are systemd's way of naming system states and grouping units into those states. If you have heard older language like runlevels, targets fill a similar conceptual role while fitting into a dependency graph rather than a simple numeric level. A target can represent a desired environment, such as a multi-user state where network services and login capability are available, or a graphical state where a desktop environment is running. Targets do not usually do work directly, because they are not processes, but they can pull in other units, meaning that reaching a target implies starting a set of services, mounts, and other supporting units. This is a powerful abstraction because it lets you say, the system should be in this state, and systemd figures out what needs to run to get there. At exam level, the most important idea is that targets are milestone-like units that define what a normal operational mode looks like. When troubleshooting boot behavior, targets help you reason about what should be active and what might have prevented the system from reaching the desired state. Dependencies are the glue that makes systemd's unit model useful, and they are also the reason systemd can start many things in parallel without breaking order requirements. A dependency expresses a relationship between units, like one unit needing another to be present, started, or active before it can succeed. The simplest dependency concept is that some services require the network, or some services require a mount, and systemd needs to order startup accordingly. Systemd uses dependency information to build a graph, and then it can start independent units concurrently while respecting required ordering. For beginners, this is a big step up from the idea of a single startup script that runs line by line. It also means failures can propagate in understandable ways. If a required unit fails, dependent units may not start, and the system might not reach its intended target, which gives you a chain to follow when you diagnose why something is missing. Another exam-relevant concept is the difference between a unit being started now and a unit being enabled for future starts. Starting a unit is an immediate action, like bringing up a service in the current session. Enabling a unit means configuring it to be pulled in automatically during boot or when a target is reached. This matters because people sometimes start a service, see it running, and assume the problem is solved, only to discover it does not come up after a reboot. The systemd model distinguishes current state from intended future behavior, and enabling is how you express that future intent. Targets are often involved here, because enabling a service generally means it is linked into a target, so that when the system enters that target, the service is included. At exam level, you should be able to reason about this difference without needing to recite syntax. The concept is that systemd manages both immediate actions and persistent policy. It is also useful to understand that dependencies can be strict or more flexible, and that flexibility influences how failures look. A strict dependency means a unit cannot reasonably function without another unit, like an application that requires a database connection to start. A more flexible relationship might be about ordering, where it is helpful to start something after another unit, but not absolutely required for the first unit to run. These distinctions matter because they influence whether a failure stops the boot process from reaching a target or merely reduces functionality. For beginners, a good mental habit is to ask, if this prerequisite is missing, should the dependent unit refuse to start, or can it run in a degraded mode? Systemd can represent both kinds of relationships, which is why it can manage complex systems while still allowing partial functionality in some scenarios. Exam questions often embed this idea when they describe a system that boots but lacks a particular service, suggesting that some dependencies were not critical for the overall target. Because systemd is a coordination layer, its units also serve as documentation for how the system is meant to behave. When a unit declares its dependencies, it is telling you, this is what I expect to exist for me to work correctly. For a beginner, This can be comforting because it means the intended relationships are not hidden inside someone's memory. It also means that when something breaks, you can often reason about what should have happened by following dependency chains mentally. If a web service is not reachable, you might consider whether the service itself is running, whether it was enabled, whether the network target was reached, and whether required mounts are present. This is not about typing a sequence of commands. It is about understanding the structure of system boot and service orchestration. The more you practice thinking in dependencies, the more you will see that many Linux failures are not random. They are consistent outcomes of missing prerequisites. That is the kind of mindset Linux Plus aims to build. Timers, mounts, and services also interact in real-world patterns that help you remember the concepts. A timer might trigger a service that performs housekeeping, which might depend on a mount being present because it writes logs or rotates files in a directory that lives on separate storage. If that mount is not active, the housekeeping job might fail or might write to the wrong place, causing storage to fill unexpectedly. In systemd terms, those relationships can be expressed so the timer-triggered service is ordered after the mount and requires it to succeed. This is a simple example of why systemd's unit model is unified across different types. The same dependency and ordering logic applies whether the unit is a long-running daemon or a one-shot task. At exam level, it is enough to understand that systemd tries to make these patterns explicit and that the unit graph is the map of system behavior. If you can picture the map, you can predict where failures will cascade. Targets also help you understand why a system might behave differently depending on how it is booted. If a system is configured to reach a basic multi-user target, you might get networking and command line login, but not a graphical environment. If it is configured to reach a graphical target, it should pull in additional services related to a desktop and display manager. If something prevents the system from reaching the expected target, the system can appear partially functional, which can confuse beginners who expected an all-or-nothing outcome. The system might boot into a minimal state because a later dependency failed, and your job is to identify the missing link. Thinking in targets helps because it clarifies what the system was trying to become. A target is not just a label, it is a statement of desired capability. When a target is not reached, it often means a dependency chain was broken somewhere along the path. To conclude, systemd's value at exam level is not in memorizing a pile of syntax, but in understanding how it models a Linux system as managed objects with relationships. Units are the building blocks, and they come in types like services, timers, mounts, and targets, each representing a different kind of thing systemd can coordinate. Targets represent system states and group units into meaningful operational modes, while dependencies describe how units rely on each other for correct startup and functioning. The modern boot process is best understood as a dependency graph that can run things in parallel while still respecting ordering and prerequisites. When something breaks, the most productive mindset is to ask what unit should have been active, what it depends on, and whether the system reached the expected target. If you can reason about that unit graph clearly, you will be able to interpret many Linux service questions with calm logic instead of guesswork, and you will be prepared to understand later troubleshooting topics that build on the same foundation.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.